connected subsets of a real line with the usual topology. So before we dig into that concept, we are going to first define what an interval is. So let A be a subset of R, let A be a subset of R, then A is an interval, A is an interval. If A is an interval, if there exists at least two distinct, points in A, i.e., that is to say, if there exists A and B in F, with A they are distinct, they are different, with A different from B, and if A is less than B and C is a point, if A is less than B and C is a point, such that A is less than C is less than B, then C is in F. So that is the definition of an interval. If there exists at least two distinct points, and if A is less than B and C is a point which is in between A and B, then C should lie within F. Now we are going to look at connected subsets. Let us first evoke the simple lemma. So lemma, how does it state? So for this case, we are going to let A be a subset of R. Let A be a subset of R. Suppose that A is not empty. Suppose that A is non-empty and A is not equal to R. Suppose that A is a non-empty subset of R which is not R. Suppose that A is a non-empty subset of R which is not R. Let me put a comma here. Non-empty subset of R which is not R, and this A is not a singleton. A is not a single point set. Then A is connected if and only if A is connected if and only if A is an interval. So what are we saying here? If A is a subset of R such that A is non-empty, A is not a singleton. I think I should remove this because if A is just a subset of R without this, without that, then that means that A is not equal to R. So we cannot have this situation. But anyway, so suppose that it's not an empty set and it's not a singleton, then A is connected if and only if A is an interval. We know, I think in the previous sessions, we have seen that the empty set is vacuously connected. Also, a single point set is connected since it only has one point, you cannot separate it. So a single point set is connected. Now, if A is not an empty set and it's not a single point set, then it will be connected if at all it is an interval. That's what we are going to see. So we want to prove this important lemma. How are we going to prove this? It's an if and only if statement. So suppose that this is the proof. Suppose that A is connected. Suppose that A is connected, and we are going to prove the forward direction by contradiction. Suppose that A is connected and A is not an interval. Suppose that A is connected and it's not an interval. So if A is not an interval, this implies that there exists distinct points in A. There exist points A and B in A which are distinct, and if C is a point, and if C is a point, and if C is a point such that A is less than C, less than B, comma, then C is not in A. If A is an interval, then C would lie in A. But since it is not an interval, we have distinct points. And if C is a point such that A is less than C, less than B, then C is not in A. So how can we interpret this? It's like we are saying that now A is not an interval. It's like a set which is a finite set which is of this form. It's a finite set which is of this form. These 2 points, between these 2 points we have a point C, but that point C cannot lie within this set. So we have that. Now I think I should also come up with a pictorial. So we have our point A is there, our point B is there, then C is in between there, and this point here is in A, this is in A, also this is in A. These 2 points, but C is not in there. So I'm going to define something. I'm going to define open sets. I'm going to define WA to be a set containing, WA is a set containing elements in A, containing elements in set A, WA containing elements in set A, such that those elements are less than C. Because C is not there in set A. It's like now this is my WA. WA consists of elements in set A, and those elements, particularly for this video, that element is element A. This is the set containing element A. This one in particular, the set containing element A. It is consisting of elements in A such that those elements are less than C. Similarly, we are also going to define WB. Now this is the set containing element B, this set here. So this is X in A such that X is greater than C. Such that X is greater than C. So what do we observe? Observe that WA now is equal to, WA is equal to because it contains this WA contains element A. Which element A is in set A? Is in set A. So WA is A is set A intersected with set A intersected with this region, with this region which contains points from negative infinity up to point C. Then also WB, it's A intersection C up to positive infinity. So observe that the other observation is that WA and WB, they are non-empty sets. Why are they non-empty sets? WA contains point A, WB contains point B. So you observe that they are non-empty. Then they are open. They are open sets. They are open sets. They are open sets in A. Where are they open sets in A? Remember, A is a subset of R. A is a subset of R, so we are in the subspace topology. This is an open set in R, also this is an open set in R. So A intersection an open set in R forms an open set in the subspace topology. So these are open sets in A. They are open sets in A. What else? What else? They are open sets in A. Moreover, WA intersection WB is equal to A intersection negative infinity C intersected with A intersection C positive infinity. So this is equal to A intersection negative infinity C intersection C positive infinity. Remember, this and this cannot meet. So this is A intersection an empty set, which is equal to an empty set. So WA and the WB at this joint. WA and WB at this joint. Then what else? They are disjoint and their union. Their union is actually set A. I don't know whether you agree that WA union WB is equal to A intersection negative infinity C union A intersection C positive infinity. So this is equal to this is equal to what? This is equal to A. This is equal to A union what? This is equal to A union. I have to be careful with this thing. It's A union. A moment. This is A union negative infinity C union C. I think this is intersection. Yes, it's intersection. We have that. And A intersection, this is the sample space. This is now A intersection R, which is A. So you observe that WA and WB, they are disjoint open sets whose union is A. So WA and WB form a separation. the formal separation of A, implying that A is not connected. Implying that A is not connected. So this is a contradiction of the fact that A is connected. So our original assumption was wrong. So implying that A is an interval. So what have we proved? We have proved that A non-term interval implies that A is not connected. A non-term interval implies that A is not connected. So an interval, a non-term interval implies that A is not connected. So if A is connected, contrapositive, if A is connected, then that should imply that A is an interval. So we are going to look at the converse direction in the next session.